Hello, ladies and gentlemen, and welcome to our YSI webinar titled How Conductivity Sensors Work, Principles and Practice in Water Quality Monitoring. My name is Michael Watt, and I'm your host tonight, or this afternoon, or this morning, wherever you might be in the world. Next slide, please. For those of you who have attended our other webinars within the series, thank you so much. I noticed that there are a few of you who have actually attended all 6. For those of you who are new, today's conductivity webinar is the 6th and final part of our YSI webinar series on how sensors work, in which we cover various parameters within water quality monitoring. Next slide, please. If you are new, if this is your first time to the YSI webinar series, and you've missed the earlier presentations and you certainly have an interest in them, don't worry. We do record all of our webinars. We've recorded how anti-fouling works, how algae sensors work, how turbidity sensors work, how pH and ORP sensors work, and how dissolved oxygen sensors work, which was held last week. All of the webinars can be accessed via our webinar library on the link on this slide. We will also be sharing this link with you in a follow-up email today, approximately 30 to 60 minutes following this webinar. Next slide, please. For those of you who are new, just a very quick review of the GoToWebinar interface, which now sits most likely on the right-hand side of your screen. There are 3 sections. The top section is for your audio settings. The second section is for questions. We will be holding a Q&A session at the end of this presentation, and you are invited to participate. Simply type your question into the question box, and we will follow up on them at the end of this presentation. The box at the bottom is for chat. These are for any technical issues that you might have. These chats come directly to the staff in the background who are hosting this webinar and can support you with any of your GoToWebinar technical issues. All right, on to our main presenter today. I'd like to introduce Zack Henderson. Zack has a Bachelor of Science in International Business at the Wright State University. He's been with YSI for 3 years as a product manager in environmental monitoring systems, but he has 10 years experience working with environmental monitoring technology. And with YSI, he's been focusing on water quality monitoring instruments, particularly our XO Zone series. Now, before we bring Zack on, I'd just like to quickly go over our agenda for today. We'll be discussing what is conductivity and why is it important, differences between conductivity, specific conductance, and salinity, principles, how conductivity sensors work, and finally, we'll be talking about real-world monitoring examples. All right, so our first section, what is conductivity and why is it important? And before we begin, we'd like to launch our first poll question. Why do you monitor conductivity? If you've never used our poll question before, the system is very simple. This screen is actually sitting on top of the presentation. Feel free to roll your mouse over the answer you'd like to select and just click your mouse. And while we're waiting for our audience to respond to our first quick poll question, I'd like to take this opportunity to bring Zack on stage. Zack, thank you very much for joining us today.
Great. Thank you so much for that introduction, Michael. I'm excited to be here.
And I understand that you just woke up. It is approximately, what is it, 7 a.m.?
Yeah,
over
just
there?
a little after 7 a.m. And I didn't quite I roll out of bed. I've been up for a few minutes here, so.
Well, we certainly appreciate your support in this presentation, waking up at such an early hour.
Thank you. Yeah, I've had my coffee, so
You're caffeinated.
I'm caffeinated.
All right, it
Okay.
looks like our audience has finished answering the poll. So why don't I share that for everybody to see? What do you think of these results, Zach?
Let me see.
Looks like we,
Yeah, it looks like mostly oceanographic studies, which is not too surprising here. Some freshwater studies, which is good, and water treatment. Yeah, a good mix. The good news is it looks like there's a little bit of interest from all the options we had here, all the segments. So that's great. Nice little diverse audience.
terrific. Okay, I'll hide this and let you continue.
Great. Okay, so again, thank you everyone for being here. I want to first talk about, well, do you know what conductivity actually is? When I say conductivity, are you aware of what conductivity actually is? So I'm going to talk first about what is conductivity, and to start, it comes from conductance. So broadly speaking, conductance can refer to any substance's ability to conduct something. The substance could be a solid, liquid, or gas. The something could be heat, electricity, or sound. So for the purposes of this webinar, we'll be focusing on water as the substance and electric current as the something. So conductance is the inverse of resistance. With Ohm's law, we know that resistance equals the change in potential, voltage across 2 points, divided by the current. To use a very basic diagram, current is applied to an electrode. At the start of the gap, there is no change in potential. As the current travels across the gap through ions in the water, by the time it reaches the other side, there is a loss in potential, in this example, a loss in potential of 10. So the resistance here can be calculated to 0.5. So let's just assume there is not a gap. The potential across an ideal conductor is proportional to the current running through it. So there is no change in current or potential from point A to point B. But if we introduce a gap and submerge this in a liquid, liquid is not a perfect conductor, so we do get a measure of resistance. Tying this back to conductance, again, it is simply the inverse of resistance. So using our example here, conductance can be calculated to 2, which is the same as 1 over 0.5. But 2 what exactly? Conductance is measured in mhos, or Siemens. Mhos are equal to Siemens. Since conductivity is the inverse of resistivity, an ohm is a unit of resistance. Mho is simply ohm backwards. As measured, conductance is defined as the ratio of current in a conductor, the conductor being liquid, to the difference in electrical potential or voltage between its ends, the electrodes here. But the measured value is dependent on the cell geometry. So the difference between conductance and conductivity involves the length of the conductor. In our industry, the standard is 1 centimeter. So it's the measure of conductance in Siemens through a 1 centimeter cube of liquid. This is how we get our units. Remember, conductance is measured in Siemens. Siemens is a very large unit with respect to water quality, at least in natural waters. So instead, we refer to millisiemens or microsiemens. 1 millisiemen equals 1,000 microsiemens. And since conductivity is per unit of conductor length, the units we use are millisiemens per centimeter or microsiemens per centimeter. So this is all a long-winded way to explain conductivity as it relates to water quality is the property of water measured through a specific cell geometry that allows it to conduct an electric current. But what actually allows water to conduct an electric current? Ions. This property relates to the amount of ions in the water. Generally, the more ions, the higher the conductivity. So liquids with low ionic strength, like DI water, have very low conductivity. Liquids with higher ionic strength, like seawater, have higher conductivity. This is interesting to think about. For example, when I was a child, I always thought that all water had a really high conductivity. I've seen the warning labels on a hairdryer, for example, and if you drop it in the tub, you'll get electrocuted. And this is pretty much true, so please don't try this at home. However, if you have water or another liquid with absolutely no ions, it would not conduct electricity. For example, there are some organizations with massive computer server warehouses that utilize immersion cooling, and this involves submersion of circuit boards directly into a non-conductive liquid. So now that we know what conductivity is, I want to discuss what influences it. There are two major factors: dissolved salts and other inorganic compounds, and temperature. Generally, more dissolved salts or solids equal higher conductivity, but not always. If we are talking about inorganic compounds, these include anions such as chloride and nitrate, and cations such as sodium and iron. These will increase conductivity. Organic compounds, on the other hand, such as oil or sugar, do not conduct electric current, and in some cases can actually lower conductivity. The other big factor is temperature. Conductivity is highly dependent on temperature, both the actual and reported conductivity. Now, what do I mean by that? What I mean is as evaporation occurs, the amount of water in a sample decreases, but the amount of ions could stay the same. So then you get a higher ionic concentration in that water, all other things being equal. The amount of ions per standard unit of water has increased, hence higher conductivity. Additionally, the temperature of a sample after it has been pulled affects the measured value. For example, let's say we have two of the exact same samples of water at the same temperature. Their conductivity readings are identical. In this case, 500 microsiemens per centimeter. Then we take these samples and we increase the temperature of one and decrease the temperature of the other. As the temperature changes, all other things being equal, the amount of ions in these samples haven't changed. But since ions move faster at higher temperatures, they become more conductive. Hence, you receive a higher measured value than the lower temperature sample. Therefore, it is very important to report conductivity at the temperature it was measured. I've included this slide for reference so you can see typical conductivity values in various types of water. Remember, 1 millisiemens per centimeter equals 1,000 microsiemens per centimeter. Ultra pure water has less than 1 microsiemens per centimeter, while seawater can have over 50,000 microsiemens per centimeter. So why do we care? Well, because conductivity is actually one of the most important and widely used indicators of water quality. Think about it. The ionic concentration of water is due to what is or isn't in the water. As it relates to monitoring, water bodies tend to have relatively stable ranges of conductivity that, once established, can be used as a baseline for comparison with regular conductivity measurements. Significant changes in conductivity data can be used to detect contaminants from discharge or some other pollution. For example, let's consider a stream. Discharges to streams can change the conductivity depending on their content. A failing sewage system, for example, would raise the conductivity level because of the presence of chloride, phosphate, and nitrate, while an oil spill could potentially lower conductivity since oil is an organic compound. Conductivity is important across a wide variety of applications. In industrial applications, to measure ultra-pure water, concentrated salt solutions, acids, and alkalis. In coastal applications, to measure salinity of brackish and seawater. In freshwater applications, such as river basin monitoring, agricultural runoff can often be detected because of pesticides and fertilizers, increasing the conductivity of the water. Additionally, road salts from winter snowmelt can threaten aquatic life. And that brings us to another reason why conductivity is so important. It factors into other critical water quality parameters, such as dissolved oxygen. The solubility of oxygen decreases as conductivity in the water increases. This means we can see fish kills due to suffocation as a result of too much salt runoff. Many other parameters are derived from conductivity, obviously specific conductivity and salinity, which I'll get to in a moment, but also total dissolved solids, or TDS, and water density. It is important to note that while conductivity can be referenced as a surrogate for some of these parameters, it is not a perfect correlation. Some additional work is required by the user, for example, to determine the TDS constant in order to achieve representative values. So now let's discuss the difference between some of these parameters. But first, let's have another question. Which conductivity-related parameter are you most interested in measuring? We'll just give a few seconds here to collect some answers. Okay, we're almost halfway through voting. I'm going to give it a few more seconds here and make sure everybody gets a chance to vote. Okay, we've closed the poll, we've locked the poll, and now hopefully you can all see the results here. Okay, so looks like for the most part, most of you are interested in salinity, and this kind of correlates back to those oceanographic studies folks. I imagine probably care about salinity, and this is good because I'll discuss salinity here shortly. Specific conductance I'll also discuss, and I'm actually a little surprised that there's quite a bit of total dissolved solids interest here as well. So I'll make sure to talk about total dissolved solids and emphasize I guess some important factors there a little bit more moving forward. So to move forward, let's just do a quick review. Conductance, as discussed in the last section, is the property of water that allows it to conduct an electric current. Conductivity is the property of water measured through a specific cell geometry that allows it to conduct an electric current. So as this relates to sensors, the measured conductance value is normalized to 1 centimeter, and normalization occurs by using the cell constant. And I'll talk about this more in the next section. So, specific conductance is the property of water measured through a specific cell geometry at or compensated to a specific temperature that allows it to conduct an electric current. So as this relates to sensors, the measured conductivity value is typically normalized to 25 degrees Celsius. Normalization occurs by using the temperature coefficient, and I'll discuss more on this in the next section as well. So another way of thinking about specific conductance is that it removes the temperature factor and allows us to just focus on the ions. Those reporting specific conductance can determine at a glance if changes are occurring in the ionic content. Also, now is a good time to mention that as we describe specific conductance, we are doing so as it relates to temperature compensation, and this is often used interchangeably with the term specific conductivity. So just to reinforce my point, specific conductance can be more useful for comparing conductivity between different locations and different times. As we discussed last section, conductivity is highly dependent on the sample temperature. Therefore, it is pretty much essential to report your conductivity readings at the sample temperature. However, if a bunch of people in an organization are reporting conductivity, it is very, very likely that they are not all at the exact same temperature. So comparison of this data from those different people can be a bit more challenging. Specific conductance compensates for differences in these sample temperatures. As it relates to measurements, specific conductance is conductivity measured at or compensated to a specific temperature. Usually this temperature is 20 or 25 degrees Celsius. The default for YSI sensors is 25 degrees Celsius. Compensation occurs by calculation using the measured conductivity with the measured temperature and the temperature coefficient. So another way to think about this is that conductivity is the true conductivity of the sample as it's measured. Specific conductance is the temperature compensated conductivity for comparison. So if you are interested in conductivity for any comparison studies or for regulatory purposes, we recommend reporting specific conductance. Okay. And let's move on to salinity. This is the most popular parameter in our poll question. Salinity is the amount of salt dissolved in the water. This value is proportional to conductivity as it directly relates to the ionic content of the water. More dissolved salts means higher ionic strength. Salinity is particularly important to oceanographic studies as it is a major influencer on the ocean's circulation. Salinity, along with temperature and pressure, affect water density. As density changes, we have rising and sinking water masses moving the water in the ocean. Also, the ocean is effectively a very large buffer, so a tiny change in salinity can be an indicator of something major happening. Historically, and still currently by some users, salinity is reported in parts per thousand. This is because it was measured by chemical analysis through titration and evaporation. However, this has since become inefficient with the advances in electrical conductivity meters. Salinity as it relates to our instruments is a calculated parameter based on the conductivity and temperature readings. Also, it's become more common to report based on the practical salinity scale. This reporting is actually unitless. However, some equipment will apply the unit PSU. So for our purposes, PSU is equivalent to PPT for measuring salinity. I do want to touch briefly on resistivity, even though no one in this audience seemed to be interested in it. But resistivity, as you remember, is the inverse of conductivity. So remember the ohm and mho. Resistivity is measured in ohms per centimeter. Okay, and now for the folks that are interested in total dissolved solids, I do want to touch on this as well. Total dissolved solids basically measures all of the dissolved substances, inorganic and organic, present in a liquid. This generally tracks pretty well with conductivity, but it is not perfect, and it requires the user to do some additional work to achieve accurate readings. So if you're using our instruments, there's a TDS constant, so it is very important to find the TDS constant of the water being measured. I want to bring this up because I want to make sure people are actually using this parameter correctly. YSI instruments have a default TDS constant, but it really should be updated to get truly representative and meaningful data. And you can refer to the instruction manual of our instruments to figure out how to properly update and determine the TDS constant for any given sample. Okay, so speaking of our sensors, now I want to move on to sensor technology and principles of operation. But first, let's have another question. What range of conductivity values do you measure? And we'll just give some time here for everyone to answer this question. Okay, we're a little bit halfway through with voting. Looks like there's still some folks out there answering. Just another few seconds. Okay, so I can see the results here, and looks like the poll is closed. So hopefully attendees, are viewing the results, and it looks like we have again a little bit of everyone here, which is great. A lot in the 0 to 1,000 microsiemens range, which typically is fresh water actually, but a nice even spread kind of through the ranges in conductivity, at least in natural waters. The lowest amount here is extremely high conductivity ranges, which occasionally is possible in natural waters, but a lot of these could be a lot of these higher values could be seen in industrial applications or laboratory applications as well. Okay, so moving on. All right, in this section, I'm going to discuss principles of conductivity measurement, types of conductivity cells, the length and area of the conductor, the cell constant, the temperature coefficient, and then I'll finally get into specifically how YSI sensors work. So first off, let's review how conductivity sensors work. So conductivity, principle by which instruments measure conductivity. So if we take a very basic example, a sample of water, electrodes are placed in the sample. You can see these gray things here as the electrodes. An electrical current is driven through them, and since the liquid is conductive, we see the current measuring through. And the results are calculated as the change in potential as it's measured across the sample. So this is a very basic way of kind of visualizing how the conductivity electrodes are functioning. Okay, so voltage is measured and conductivity is calculated. Again, this is a very simplified explanation. Think of the conductivity cell as the sensing area. This cube, for example, Generally, conductivity cells consist of electrode pairs to which current is applied and voltage is measured, and that allows conductivity to be calculated. The classical conductivity cell consists of two electrodes with a measured range which is typically restricted to lower conductivity levels. There are some limitations with this design, this two-electrode design. An effect known as polarization can occur between the electrodes and the liquid, which leads to the display of artificially lower values. As current is applied, positive ions are attracted to the negative electrode, and negative ions are attracted to the positive electrode. This can affect the measured value. This can be mitigated to some degree by alternating the current between the electrodes. The anode becomes the cathode, and the cathode becomes the anode, and vice versa. This is done very rapidly. The oscillation between the negative and positive means that the cations and the anions oscillate about their location with the applied frequency. Think of this kind of like a tug of war between the two electrodes. So this mitigates all the negatives from sticking to one electrode and all the positives sticking to another electrode. So despite these countermeasures, polarization effects cannot be completely avoided when measuring high ionic concentrations with a two-electrode cell. The four-electrode conductivity cell has a drive electrode pair in addition to the sense electrode pair. Think of the pair in the middle as dedicated independent voltage electrodes. This design compensates for coating and buildup, which makes it relatively unaffected by polarization. These cells usually have a wider measurement range, but may not be quite as accurate as the two-electrode cells in ultra-pure or low conductivity solutions. Now that we've discussed two common cell types, let's talk about the length of the conductor. Remember, conductivity can be defined as conductance per unit of conductor length, the conductor being the sample liquid. The industry standard unit of conductor length is 1 centimeter cube of liquid. The 1 centimeter cube is the theoretical or ideal conductivity cell. Think of the sensor conductivity cell as the sides of the cube. This is the sensing area. The cell geometry affects the measured value of the sample, but not every conductivity sensor is designed to measure precisely 1 centimeter cube of liquid. So how do we account for this? So this is where our conductivity cell constant comes into play. It is important to note that the cell geometry defines the cell constant. This can vary between different types of sensors. Sensors come in all shapes and sizes, so we need to apply the cell constant in order to obtain comparable and meaningful data. The cell constant is the actual distance between the electrodes in a sensor divided by the cross-sectional area of the electrodes. This might sound confusing, but I'm going to explain it here right now. So, for example, our theoretical conductivity cell is 1 centimeter over 1 centimeter squared. This gives us a cell constant of 1 per centimeter. Now, this example, our conductivity cell is 1 centimeter over 4 centimeters squared. Using the calculation, this gives us a cell constant of 0.25 per centimeter. And finally, one more example. This conductivity cell is 2 centimeters over 1 centimeter squared. This gives us a cell constant of 2 per centimeter. So this all just goes to kind of illustrate that, again, different conductivity sensors can have different geometries, which can result in different cell constants. So now that we know how our cell constant is determined, we can apply it to determine our conductivity value. To ensure conductivity cells of different shapes and sizes can generate comparable data, sensors multiply the conductance by their cell constant. This results in the conductivity value. So let's look at an example sensor from a previous slide. This sensor measures 100 microsiemens with its conductivity cell. Remember, this sensor's cell constant is 0.25. So using the calculation, we can determine the actual conductivity value that is being measured is 25 microsiemens per centimeter. The cell constant is relatively stable, but it will drift over time with use. Every time we submerge the sensor, the cell can experience some buildup. Or even after cleaning it with a conductivity brush, we are changing, if ever so slightly, the surface of the electrodes and in turn the conductivity cell itself. So the cell constant must be updated to account for this change. And this is why we calibrate. When we calibrate, we update the cell constant based on the changes in the cell. If you are using YSI software or a handheld, every calibration report will display the new cell constant value, which is great for tracking changes to the sensor. Finally, the last important factor in all this is the temperature coefficient. Again, conductivity is strongly dependent on temperature. It can vary up to 3% for a single degree change in temperature. The temperature coefficient is equal to the percent change in conductivity for each degree Celsius change in temperature. This value varies depending on the composition of the sample, but can be determined from published data or by looking at measurements of representative samples. So here's another example to clarify this. Here we have a conductivity standard solution. At 25 degrees Celsius, it reads 1,413 microsiemens per centimeter. At 26 degrees Celsius, it reads 1,440 microsiemens per centimeter. So we determine the conductivity value increased by 1.91% per 1 degree change in temperature. So the temperature coefficient is equal to 0.0191. And this is actually the default value for YSI EXO and Pro Series temperature coefficients. And this is why it is important, why this is important is it allows for the calculation of specific conductance, as we talked about in the last section. And we can verify this by plugging these numbers into the specific conductance formula. Now I want to review how sensors work, specifically YSI EXO sensors, because that's my product line, of which we have two types, a non-wiped or standard conductivity sensor and a wiped conductivity sensor. First, let's look at the non-wiped sensor. This sensor features a wetmate connector, titanium housing, a built-in thermistor, and it uses a 4 nickel electrode cell. As this is a smart sensor, it features an internal circuit board that processes the signal and saves calibration information. Functionally, this sensor works just like our earlier example. Water flows through the cell, current is applied to the electrodes, voltage is measured, and conductivity is calculated. Now let's look at the wiped conductivity sensor. This also features a wet mate connector, titanium housing, and internal circuit board. But the thermistor is embedded on this one, so you can't actually see it. And this one uses 4 graphite electrodes rather than nickel. You'll notice the unique open cell design, which allows the sensor to be cleaned with our anti-fouling wiper. Again, the same measurement principles apply here. Okay, so let's move on to real-world applications. But before we get into this, we'll have another question. What concerns you most about monitoring for conductivity? We'll just give a few seconds here to allow people to answer. Okay, we're just over 50%, so if you haven't voted yet, please do. Okay. All right, well, thank you for participating there. And you can now see the results. So proper calibration, certainly, sensor maintenance and sensor drift and fouling. These are all things that you should be at least aware of and concerned for when you're wanting to make conductivity measurements. So fortunately, I'm going to discuss each of these. Okay, so in this section, I'm going to talk specifically about an application from, in the United States, the Maryland Department of Natural Resources. And then I'll cover some challenges with continuous monitoring, choosing the right conductivity sensor, choosing the right calibration standard, and then I'll finish out this webinar with some best practices, tips for calibration and sensor maintenance. All right, so first, the Maryland Department of Natural Resources did a road salt study. So as we've touched on, stormwater can carry accumulated road salt into storm drains and into surface waters. Maryland DNR deployed conductivity loggers upstream and downstream from an interstate to monitor the effects this has on the environment. On this graph, we can see specific conductance readings from 2 sites in the Savage River watershed, one upstream and one downstream from Interstate 68 in Garrett County, Maryland. The upstream readings are represented here by a green line. We consider this the baseline, as upstate from the interstate, or as upstream from the interstate is pretty much unaffected by the road salt runoff from the interstate, while the dark blue line represents the downstream readings, which appear to be greatly affected by the road salt runoff. The dark red bars represent snow precipitation. On this graph, we see the relationship between stream flow and specific conductance. We can see after a large snow event, there may be some lag, but then conductivity spikes as salt enters downstream. We then see drops due to higher flows, which typically means greater dilution. You may also have noticed a conductivity increase in the summer months during the low flow season. This may be because there is little opportunity for dilution. So now that we've seen results of a long-term deployment, let's look at the challenges to continuous conductivity monitoring. And really, we're talking about one thing in particular. Can anyone guess what that might be? Fouling. That's right. The buildup of material which can affect the sensor performance. The longer the sensor is deployed, the greater the effects of fouling. Remember, when we were talking about the conductivity cell changing as it's being used, this buildup can change the physical geometry of the cell. And unfortunately, the non-wiped conductivity sensor is more susceptible to the effects of fouling. This salinity plot shows fouling drift of the non-wiped conductivity sensor compared to the wiped conductivity sensor over 47 days of deployment. This information is also showcased in our Fighting Fouling case study, which is linked here at the bottom. If you haven't seen this yet, I highly encourage you to check it out. But as you can see on this slide, wiped conductivity sensor stays relatively clean after the deployment, as opposed to the standard non-wiped conductivity sensor. But there are applications where the non-wiped conductivity sensor is the better solution. So how do we choose the right conductivity sensor? Well, it really depends on your application. Now, if there are those listening that do measure conductivity in laboratory applications, you may have more options to consider. You would want to take a look at our laboratory solutions. But since this webinar is focused on outdoor water quality, I'm going to cover the two sensor options we've discussed for the YSI EXO platform. So first, we have our standard or non-wiped conductivity sensor. This just so happens to be the same type of sensor that's also used on our ProDSS sampling platform. And there is a reason for that. It is a better sensor for sampling and, in particular, rapid profiling applications. This is mostly due to the built-in thermistor, which has a quicker response time than the thermistor that is embedded in the wiped sensor. Additionally, as we discussed in our last section, due to its unique cell design, this sensor has a larger cell constant, which actually affects its range and accuracy. This sensor has a wider measurement range than the wiped conductivity sensor, going up to 200,000 microsiemens per centimeter. So those of you in that very high, there were a few in that very high measurement range, would be more interested in this sensor. Anyone that is interested in monitoring in extremely high conductivity environments, this is the sensor for you. And additionally, at least on paper, this sensor does have a higher reported accuracy. However, before moving on, it is important to note that while on paper it does have a higher reported accuracy, this sensor does, as we've shown in the case study, it does become affected much quicker by the buildup of fouling over time, which generally makes its use limited in continuous deployment applications, depending on the type of environment, if it's a high fouling environment or a low fouling environment. And this is where the wiped conductivity sensor really shines in those higher fouling environments. Its open cell design, again, allows for the wiper to clean the electrodes directly and minimizes fouling. It does have a smaller cell constant that limits its effective measurement range to top out at 100,000 microsiemens per centimeter, which still covers most natural environments. Additionally, its embedded thermistor is not quite as responsive as the non-wiped sensor, making it less suited for rapid profiling applications. So while on paper the non-wiped conductivity sensor has a higher accuracy, if your application involves long-term monitoring, particularly in a fouling environment, this is definitely the sensor you want to choose. So now that we've talked about choosing the right conductivity sensor, I want to discuss choosing the right calibration standard. The general rule of thumb is to pick a standard closest to your expected measurement value. And this is what YSI recommends. However, I will add one caveat. For most applications, we do not recommend calibrating below 1,000 microsiemens per centimeter. Why, you might ask? Well, there's a couple reasons. Even a 1,000 microsiemens per centimeter solution is extremely easy to contaminate. So calibration solutions below that can be unreliable without the highest level of standards in place to prevent contamination. I mean working in a controlled laboratory environment with all sterile equipment. Otherwise, that solution in the bottle labeled 100 microsiemens per centimeter will have changed by the time it is poured into the calibration cup. 2, we recommend a minimum level of ionic strength in order to achieve a calibration that is good across the full range of the sensor. So basically, we recommend if you're measuring in low ionic strength environments, we do recommend at least calibrating to a 1,000 microsiemens per centimeter conductivity standard. As far as best practices go, we recommend calibrating the conductivity sensor. As far as the best practices go, we recommend calibrating the conductivity before any other sensor if you have a multi-parameter sonde or meter. This isn't required, however, it may help prevent contamination from other standards. As we've just discussed, conductivity is actually one of the easiest standards to contaminate, as opposed to a concentrated pH buffer, for example, of which one drop could change the entire conductivity standard. So again, it's not necessary to calibrate conductivity first, but it is recommended if you wanted to minimize the chances of contamination. And obviously it is paramount to keep everything clean, not just the conductivity sensor, but all the sensors, the probe guard, the calibration cup, and anything else that will come in contact with the calibration solution. Clean the conductivity sensor with the included conductivity brush, and you may want to remove the wiper brush as it can accumulate contaminants. After everything is clean, perform a pre-rinse by filling the cal cup with just a little bit of standard solution and shake it around to cleanse the sensor of any leftover liquid. And you can do this for three times for best practices. Prior to actually calibrating, it is good to check the temperature readings against a high accuracy thermometer. Remember, if your temperature is off, your conductivity reading will be off too. Also, check the conductivity readings in dry air. There should be zero conductivity in air, so if you see values, make sure the sensor is really dry. You can use compressed air or just let the sensor sit out overnight. After you've ensured that it is dry, if you still see values, conductivity values, that could be a sign of leakage, and you should contact your local tech support. It is very important to keep the sensor under the same conditions or in the same state as it's going to be used, as it's going to be in when it's in use. So this means when you calibrate, keep the probe guard on. I know it is tempting to take it off, but this is shown to impact the actual readings. And finally, make sure the sensor tip is fully submerged. You should see the solution fill up to the second line if you're using the EXO calibration cup. And when you see the solution fill to the second line, you'll know that the sensor tip is fully submerged. We do recommend kind of agitating or jostling the sensor to dislodge any potential air bubbles that could be trapped in the conductivity cell, as they can skew the calibration. So conductivity is a one-point calibration. So to start, choose your standard and start the process. This image is actually captured from our core EXO software, and there are a few things to pay attention to here. So make sure the standard value matches the value on your conductivity standard. Wait for stability to turn green and say stable before applying the calibration. Check your pre-calibration value to see how far off your sensor actually is, and make sure to check your temperature value to see if that value makes sense and that it is also stable. If you are calibrating specific conductance, which as we discussed you almost always should since it compensates for differences in temperature, then you don't have to do any calculation of what the conductivity value should be at the measured temperature. So at this point in our example, let's wait for stabilization. Okay, and once it is stable, then we can apply the calibration. Once you've applied the calibration, we can see our calibration summary. And here we can view our cell constant. We can also view a full calibration report to find the cell constant. So this example shows a great cell constant of 5.1. And from that, we can determine that this sensor really hasn't drifted much at all. So just to review the calibration process, start by cleaning the sensor, then do a triple rinse of the sensor with the Cal Standard, then immerse with a fresh standard solution, then check the readings and wait for stabilization, and then you get a good QC score and your sensor is calibrated properly. Finally, I want to end on sensor maintenance and storage, which is relatively straightforward. Basically, it's good practice to clean the sensor after each use. Depending on how dirty or fouled it is, the sensor might just need rinsed in tap water and use the little conductivity brush. If it looks a little more nasty or you see some more buildup, you could use warm soapy water. And again, using that conductivity brush to clean it. And if it looks very highly fouled, you can actually soak the sensor tip in white vinegar to try to loosen up some of that accumulated buildup. And make sure you rinse the sensor thoroughly after that. As far as storage goes, the sensor is actually pretty robust and can be stored wet or dry. For short-term storage, it is certainly okay to leave the sensor installed on your sawn bulkhead and kept in a moist environment with the rest of the sensors. For long-term storage, we do recommend storing the sensor dry if you're storing for multiple months at a time. So that's it. We now have a final question for you all. Would you like someone from YSI to contact you about anything conductivity related to discuss these sensors? And I'll just give a few seconds here to allow for answering. Okay, about halfway through. Alrighty. In the interest of time, I think we can probably move it along. And at this point, while you're answering that, I'll check on some of your questions. So Michael, were you able to collect some questions for me?
I did, Zach, and thank you so much for your time with this presentation. It was terrific, very engaging, and we do have quite a few questions that have come in. Could I just get you to switch to move to the next slide, our final slide?
Thanks for the reminder.
No worries, we're a team. So for anyone out there who has additional questions that you'd like to take offline, we do have 2 email addresses here that might be of interest to you. info@ysi.com. That's a way to contact Zach directly or indirectly. And if you'd like to get in touch with a regional representative within Asia Pacific or EMEA, simply use info.apac@xyleminc.com. Again, I mentioned at the beginning of this presentation that this is the 6th and final webinar within our YSI series. And we thank everyone who has attended throughout the entire series for your time and for following us. It's just terrific, the audience we've had. But let's move on to our questions. There are quite a few waiting for you, Zach. Let's address the first one. What is the impact on other parameters without conductivity measurement?
Well, conductivity certainly, since it's directly related to the amount of ions in the water, and if you remember from the earlier slides, the amount of ions in the water are kind of related to what's dissolved or what's actually in the water. So without knowing the conductivity value, you certainly can measure other parameters, but you may not have quite as clear a picture or insight into why some of your parameters are reporting what they're reporting. For example, if you're measuring dissolved oxygen, very low concentrations of dissolved oxygen, for example, if you don't have that conductivity or salinity parameter, you may not get the full picture. If you remember my example with the salt runoff, or a lot of salt dissolved in a freshwater solution, can kind of minimize the oxygen in that and kind of create an anoxic environment, which could cause fish to suffocate, for example. So again, conductivity just gives you that little bit more insight, where if you see, oh wow, this is a really high conductivity or salinity value, then you understand a little bit more about why my oxygen levels are so low in my sample.
Terrific.
Hopefully,
Thanks.
hopefully that answers that.
Yep. Thank you for that. And in our audience today, we have Leon. Leon was asking about how to choose the calibration standard. This was just before you opened up a terrific slide on calibration standards. Your explanation was quite clear, I thought. Leon, we will be sharing this PowerPoint from the webinar on our website that's displayed here on the slide, www.xylem-analytics.asia. This will be posted tomorrow, so feel free to download it again and use it as reference. Our next question, would it be
Actually,
more, go
Michael,
ahead.
I'll just add a little bit on that, just because
Sure.
I felt at least like I kind of went through that rather quickly. But I do remember the poll results, the answers to our question about the ranges of conductivity, and there were a lot of users interested in that lower conductivity range. So I tended to focus on just making sure, if you are measuring in low conductivity ranges, the lowest standard we recommend using is, again, that 1,000 microsiemens per centimeter. But certainly if you're in higher ranges, we do have higher concentration standards that would be more appropriate for your sample.
Thanks for adding to that, Zach. Very helpful. Okay, next question. Would it be more beneficial to calibrate at multiple points for conductivity?
So, theoretically, that would be okay. Fortunately, our YSI sensors have a very strong linear response to changes in conductivity. And what that means is calibrating at a single point will effectively calibrate the full range of the sensor. And what that means for you is you don't have to purchase more than one standard. As you know, some standards can be quite expensive, and having to calibrate frequently, then that can add up. So fortunately, the conductivity sensor design allows for just a single point calibration, and will still ensure that you get good results across the full range of the sensor.
Thanks, Zach. Can you clarify what the difference is between salinity and TDS?
Yeah, absolutely. On the most basic level, salinity is literally the measure of the amount of salts dissolved in the water, whereas TDS really can be any dissolved substance, inorganic or organic. What this means is, and I kind of touched on it earlier, it makes TDS a little bit more tricky and difficult to actually get like representative values for. It does require some extra work on the user, on the part of the user, to determine the TDS coefficient. And again, as I mentioned, there are instructions, I know at least in the EXO and ProDSS manuals, for steps to take to obtain that TDS coefficient. which is certainly what we recommend. There was a large portion of the audience that seemed to be very interested in total dissolved solids, or TDS, and so I highly encourage those folks to review the manual. And again, if it can be a little tricky, so if it still doesn't seem clear, contact your tech support for further assistance. But a TDS coefficient should be determined in each sample that you would like to measure that in. And just to tie it back to the question, that's not required for salinity. The salinity value is automatically calculated by our sensors. You don't have to do any extra work to get meaningful data.
Thanks for that, Zach. Just rereading over some of these questions, I missed a very interesting question. I'm glad I went back. Is it possible to use conductivity to assess oil spills?
Yeah, absolutely. And oil being an organic compound, as we discussed early in the presentation, we can actually see drops in conductivity levels due to the introduction of oil in a water body or sample. So, if you're doing baseline stream monitoring and there would happen to be a spill, you might actually see a significant drop in the conductivity readings or data, and that could be correlated to that introduction of oil. So the short answer is yes.
Terrific. Okay, let's move on to our next question. Can YSI conductivity meters, such as the Pro 30 or Pro Solo with CT sensors, be used as conductivity tracers for discharge measurement?
Yeah, oh, absolutely. That's a great question. Yeah, certainly, and YSI has several options for conductivity sampling meters. I know in this presentation I largely focused on the ExoSonde monitoring platform, but as I did discuss, a lot of the principles of operation for these sensors are pretty much identical. I mean, there are differences in the two exo sensors, the wiped and the non-wiped. But the sensors that are sampling meters, like the Pro 30 or the Pro Solo with the ODO-CT, yeah, those all use a very similar conductivity cell, similar to the non-wiped or standard exo sensor. So the measurement principles that I discussed there, they apply for those sampling handhelds, and those are great options for if you wanted to use that in like a tracer application.
Terrific. We're getting quite a few questions concerning your presentation itself. People are quite interested in getting their hands on a copy. Just a tip for everybody, as of tomorrow morning, this PowerPoint will be uploaded to the website that's currently listed on our screen as a PDF in PDF format. So we do encourage you, we invite you to the site to download it at your own convenience. Okay, Zach, next question. We still have quite a few coming in. I realize that the hour is getting late. We'll just take a couple more questions. Have no fear. If you have asked a question, we will follow up offline tomorrow or later in the week. So Zach, next question. What is the best standard to calibrate conductivity probes, as our ambient seawater varies from 50,000 to 75,000?
So with that, I would certainly recommend the 50,000 microsiemens per centimeter standard. I think the next jump up in at least in our standard solution, at least in the YSI standard solution, is I think it goes up to 100. But if you're looking in the 50 to 70 or 75 range, then certainly the 50,000 microsiemens per centimeter standard solution would be the best choice there.
Terrific, thanks. Let's see, I think we'll take the last question here. Could you please explain more about the influence of pesticides and fertilizers on conductivity?
Yeah, absolutely. So fertilizers, when they're introduced to the water body, um, they're introduced in the form of phosphates and nitrates, which do increase the conductivity concentration in that water body. It's just on a basic level, just think of it as introducing more ions into the sample of water. And as you know, obviously, hopefully after this presentation, the more ions, the higher the ionic strength and the higher the measured conductivity value. So on a basic level, those fertilizers contain properties that will certainly increase the conductivity in the water body. And this in the U.S. And I'm sure in other parts of the world too, this is a pretty serious issue. You know, a lot of people are interested in not just conductivity and monitoring now, but also nitrate monitoring, just because of in the U.S. we have a lot of farmland, and over fertilization is a real concern. And when that excess fertilizer washes into the water bodies, we do see spikes in conductivity. We see drops in dissolved oxygen, and we see a lot of fish kills, unfortunately, due to this. So, yeah, it does truly affect conductivity and has a larger impact on aquatic life and the health of the environment.
Great, thanks, Zach. Again, we have quite a few questions that we haven't answered yet. Rest assured, we will follow up offline. If you have additional questions, don't be shy. Please contact us at the email addresses listed on this deck. And you will receive a follow-up email within about 30 to 60 minutes with a link to the recording, a link to a certificate. Many of you have asked to receive a certificate to prove that you actually attended today's webinar. And again, all 6 webinars will be on our website within our webinar library. Thank you all for attending. Zach, would you like to close it up for us?
Oh, sure. Thank you for the honor. Yeah, it was a pleasure. I appreciate everybody attending, and hopefully you got a lot of good information out of this. Hopefully you all learned something, and I really appreciate you all. I realize it's early for my time, but I'm sure it's getting pretty late for you guys. So I really appreciate your time and sticking with us throughout this whole presentation and throughout this whole series. This was great, and hopefully we can do something again here in the future. So thank you very much, Michael, for organizing this, and I was happy to participate and happy to be a part of it.
Thanks, Zach, and thanks to everyone. Stay safe, and we hope you'll join our next webinar. Take care. Goodbye.